Triboelectricity, Think Different, Part 4. The previous video shows that rubbed glass rod can attract paper scraps in small water flows. It suggests that triboelectricity can overcome Earth's gravity, and Earth's gravity may also be triboelectricity that generated by the friction between the magma and the crust. From Cavendish's torsion scale experiment and the similarity of gravity formulation and electric interaction equation, gravitation and electromagnetic force are very equivalent. Why can frictions generate triboelectricity? When stop the friction, where will be the electric charges? In our work and experiments, there are some operations similar to the triboelectric generation process, such as nuclear magnetic resonance test, electron paramagnetic resonance test, and power generator working process. Maybe these procedures can give us some clue. The in-M or test principle is: positively charged nuclei have spins, then they have magnetic moment. The magnetic moment is mu equals gamma s, mu nuclear magnetic moment, s nuclear spin quantum number, gamma nuclear magnetic spin ratio. When there is no external magnetic field, the nuclear magnetons in the atoms are randomly distributed. Left figure. When a strong external magnetic field is present, the sample nuclear magnetons will precess along the external magnetic field, either paramagnetic or diamagnetic. Right figure. A radio wave is emitted in the direction of the sample's nuclear spin, and varies the wave's frequency. As the radio frequency couples with the nuclear precess frequency, the nuclear in the precession is subjected by an additional magnetic field from the radio wave. The nuclear magnetic moment then absorbs the energy transfer into higher energy level. The magnetic moment flips generate in-M or signals on the recorder. This method is frequency scanning resonance. EPR, electron paramagnetic resonance, test principle is: the electrons have charges and spins, ms. They have magnetic moments, mu b. Each electron has energy E as in the equation. Here G is a physical constant, ms is the spin quantum number, value +1/2 or -1/2, indicates electron spin direction. Mu b is the electron magnetic moment in an atomic magnetic field. B is the external magnetic field. In the absence of an external magnetic field, B, nor, equals 0, electrons with different spins in an atom are assumed to have the same energy. When there is an external magnetic field, B, nor, not equals 0, the electron spin causes the magnetic moment to become a paramagnetic field, ms -1/2, or a diamagnetic field, ms +1/2. The energy difference between the two states is delta E equals E +1/2, E 1/2. A low-energy state electron with spin ms -1, 2 can absorb a photon with energy equal to delta E, and transition to a high-energy state electron with spin ms +1, 2. Obviously, the stronger the magnetic field, the greater the energy difference delta E between the two electrons' magnetic moments. In electron spin resonance testing, usually the external magnetic field is about 3500 G, and the energy difference between two different electron spin states is in the microwave range, 9 to 10 GHz. If the radiation frequency is fixed, the external magnetic field is changed, and delta E or B nor is adjusted to match the relationship shown on the left. Magnetic moment reversal will occur. In an EPR test, a sample, containing single electron radicals, is placed in a magnetic field. Fixed frequency microwaves are emitted toward the sample in a direction perpendicular to the magnetic field. The electron magnetic moment will have a certain inclination angle with the external magnetic field, just like nuclear precession. Varying the strength of the magnetic field, the electron's magnetic moment will change its tilt angle, and eventually align with the field. When the tilt angle is 0, the electron spin axis is completely aligned with the direction of the magnetic field. The electron then absorbs the radiation energy and changes from a paramagnetic, low-energy, state to a diamagnetic, high-energy, state, producing a strong electron paramagnetic resonance peak. The signal is usually expressed as the first differential value of the absorption peak. This is the field scanning resonance method. The principles of NMR and EP testing are: atomic nuclei or electrons have a magnetic moment due to the spin of the charge. When they are in an external magnetic field, their magnetic moments precess along the external magnetic field, either paramagnetic or diamagnetic. Radio waves and microwaves are both electromagnetic waves. Their firing into the sample acts like fine-tuning the micromagnetic field, in which the nuclei or electrons reside. When the radiation frequency and external magnetic field are suitable for the case of electrons or atomic nuclei, their magnetic moments absorb energy and change direction from paramagnetic to diamagnetic. Therefore, the resonance process consists of two steps. 1. Change the magnetic field strength, or change the frequency of electromagnetic radiation to couple the external magnetic field with the sample electron, or nuclear precession frequency. 2. The nuclear or electron magnetic moment flips and changes direction. A power generator has two major parts, the stator and the rotor. Both are wrapped with coils. The stator coil is energized to form a fixed magnetic field. The rotor coil rotates within the stator magnetic field. The stator coil is cleverly divided into several parts. Therefore, as the rotor spins, the electrons in the coil experience changes of the magnetic field. When the changing frequency of the magnetic field is coupled to the spin frequency of the coil electrons, the paramagnetic moment electrons are forced to flip into a diamagnetic magnetic state. A simple figure to describe the process of generating current in the rotor coil. The red arrow indicates the direction of the stator magnetic field. The blue arrow indicates the rotating direction of the rotor coil. As the coil rotates, the electrons in the coil continuously experience changes in the external magnetic field, from strong to weak, and from weak to strong. The changing frequency couples to the electron precession frequency. The coil's electron magnetic moment absorbs energy and flips its direction. When most of the coil electrons' magnetic moments are in the same direction, the charge repulsion and magnetic repulsion between them will cause them to repel each other as much as possible, thus generating an electric current, as shown by the green arrow in the figure. NMR tests, EP tests, and power generators all work by rotating the sample nuclei, or electrons, in a variable magnetic field. They resemble amplified friction reactions. When the magnetic field changing frequency is coupled to the nuclear or electron precession frequency, the nucleus or electron will flip and change the direction of its magnetic moment. This destroys the original electrical and magnetic balance between electrons and atomic nuclei. In NMR and EP testing, transient jumps release resonant signals. In a generator, the continuous production of large numbers of electrons with the same spin direction forces them to move and generate an electric current. The above three situations are very similar to the triboelectricity generation process. During the friction, electrons on the surface of the glass rod move back and forth among the silk atoms and electrons' magnetic field. Once the friction makes the glass rod electrons' spin frequencies couple with the change of magnetic environment, the electrons may flip their magnetic moments. A large number of electrons, with the same magnetic moment direction, repel each other and squeeze to the surface of the glass rod, thereby showing triboelectricity to the outside world. Once the friction stops, the magnetic moment flipped electrons will return to their original state, and the glass rod will no longer show any charge to the outside world. The process of generating electricity helps to understand Fleming's left and right-hand rules in the microscopic world. The three red, blue, and green arrows in the generator figure represent the direction of the stator magnetic field, the direction of the change of the magnetic field that experienced by electrons, and the direction of electric current respectively. These three directions can be related to Fleming's right-hand rule. In the right-hand rule, the index finger points in the direction of the external magnetic field. In the generator diagram, the red arrow points in the direction of the stator magnetic field. The thumb represents the direction in which the conductor cuts the magnetic field lines. The blue arrows in the generator diagram indicate the direction of the magnetic field changes experienced by the electrons in the rotor coils. The middle finger represents the direction in which current flows, the direction in which positive charges move, which is actually opposite to the direction in which electrons move. The green arrows in the dynamo diagram represent the repulsive force between the same direction magnetic moments of electrons, which produces an electric current. The process of producing electric current explained. 1. Why is the current always accompanied by a magnetic field? And why is the magnetic field always perpendicular to the direction of the current? Because in the microenvironment, the electron movement, current, direction is parallel to the electron spin plane. The electron's magnetic moment is along the direction of the electron's spin axis. Therefore, they are perpendicular to each other. Whether it is triboelectricity generated by friction, or current generated by a generator, they are all caused by the flipping of the electron's magnetic moment. 3. In an electric current, electrons with the same magnetic moment will automatically flow to places with low electron density and low probability of the same magnetic moment. In the absence of current, electrons with same direction magnetic moments strongly repel each other and squeeze to the surface or to the tip of a conductor. The process of making triboelectricity can be related to Earth's gravity. As the Earth spins, the crust and magma are constantly rubbing against each other due to their different speeds. It causes some electrons' magnetic moments in the Earth's crust to flip. These electrons repel each other and push toward the Earth's surface, creating a static charge on the Earth's surface. Static charges induce charges on tiny objects and attract them to the Earth's surface. In the equatorial region, the Earth's linear velocity is high. The probability of friction between the crust and the magma is high, and the probability of electron flipping is also high. In the polar regions, all these possibilities are low. Therefore, a large number of electrons, with the same magnetic moment generated in the equatorial region, are forced to diffuse and gather in the polar regions. This forms the magnetic poles of Earth's magnetic field. The polar regions have powerful electromagnetic fields that react with charged particles in the sky and display auroras. However, according to the hypothesis, electrons with the same magnetic moment generated by the friction between the crust and the magma will diffuse to the two polar regions. So the two polar regions should show the same magnetism, but this is not the case in reality. Perhaps Earth's electron diffusion is also affected by solar particles. In the polar region near the Sun, and the polar region away from the Sun, there are different diffusion behaviors. resulting the magnetic N and S poles. References. Thanks for watching. Goodbye.